这个在哪里看？
没有啊，
没有，反正这个是录屏是录什么？
录给我自己。
那个自己看。
对，
哦，对，行。
你是搬来吗？
不是，我是有同学问隔有同学隔离，我还以为是有网课还是之类的。
如果他要视频，可以让他发邮件给你。
OK，你发谢谢。
Interesting. Okay, welcome back. Today's the ranking day. The quizzes are all marked. We will discuss it in the tutorial hour. So I think some of you have friends that have COVID or either COVID or close contact. Please ask them to email me. And if they need recording, also email me. Any questions from last week? Lectures or tutorial or content? Yeah. 1.6.28. Is it the tutorial question? From which lecture? Last week? Okay, yeah. How about it? Yeah. What's your question? Yeah. Yeah. And then? The step. Do you have you tried or you don't understand about my step there? Have you tried yourself? You can't solve it? This one? You mean this? Okay. Okay, sure. So this question say that if I don't remember wrong, so you assume this and then prove this, right? Okay. So what I did is first I use universal instantiation, right? Let's see. So this one, okay, instantiate with 1C, right? This is what you can do using the rules of inferences, sorry. And then, okay, maybe, yeah, let's go this. Okay, and then how about this one? This is the contra positive together with the De Morgan's law. right? And then this one is the integration and disjunction law. Okay. And then this one repeat again. This is the second universal instantiation. So let me label it. So this one is for this. Okay. This one part two. This one part one. Right. And then what did I do? So um, oh, okay. I think I missed something out. This one. Hey, wait, let me see. Okay. Oh, this is cute. Um, this one is QC. Oh, okay. So this one because of the. Okay. So this part is true, right? So you can take true with any statement here. Right. So what is it? Can I do this? So there's a P or Q. What's this called? Remember this? Let me see. What's this? Anyone? Ah, oh, didn't share the screen. Okay, sorry. The screen is golden. Okay. Go today a bit left. Okay. Uh, yeah, I mean this law here, this one. Is there such law? For the addition law, okay. So this one I use addition. Basically, it's this one here. Okay, and then I added in, and then this one what did I do? This one is just copy. This is just a source from that to the tree from tree. Okay, and then what did I do? So I got this sentence here. Also this sentence here from associativity as well. So okay, right. And then what did I do? So why can I combine these two together? So I got with a negation of the statement, right? So what did I use? Did I use this? So, and let me see. So Now let me do something, right? So Q not and Q. Right. So I get Q and Q. Okay, so this one is not P and P is a contradiction. Q or false is Q, right? Q or false is Q, right? Right? Q or false. So I think I did something wrong here. So I should have used. Okay, I think I did something wrong here. I should have used Q or not Q, C, and Q. Okay. And then since that is the contradiction, then that one is just Q here. And then use the implication and disjunction again. Go back. And then use universal generalization. Is it? Are you following or not? Confused? Which part? Which part? Because there's a mistake here, so I'm really confused. Okay. Which part you want me to say again? This one? You mean this one? Okay. So this part here is just the universal instantiation of this one, right? So I apply X to C. Okay, this one. Okay or not? Okay. And then next, since I got this right, so I can take disjunction with anything. Okay. In particular, I take it with RC. Okay. Because why I want to do this is because I observe that I got similar thing here, right? So here is PC, not Q. So okay, I don't to simplify, I don't mention about C. So here is P or not Q, right? But here is PQ. So somehow you want to make them the same, right? So I just take and disjunction with R, which is okay because from P I can get P or Q. Is that okay? Okay, so far okay. And then next I use the associativity to move this bracket here to here. Okay. And then the other one, I do the similar, I move the bracket to here. Okay. So that I leave out this term here. Okay. And then you notice that these two look the same. Right? Is that okay? Okay. And then so here I got okay, let this be another proposition, right? So just a proposition, maybe I call it Q. And then this one confuse you again. So okay, so something like this. So okay, please don't confuse us. So I see I see the statement as like this is a statement and this is a not something, right? And then I see that another one is the same, but the other one is the negation of this one, right? Okay, is that okay? Can follow? Okay, so so you see, Q or not P and Q or P. So this is like the distributivity, right? Remember, like multiply plus. Okay, so you can pull this Q out, okay, or not P and P, right? So this one is like distribute, right? If you distribute in, you get this line here. Okay, so but not P and P is a contradiction. So it's a false statement. So Q disjunction with a false statement is always Q. This one is called the law, no, identity law. So this is this one is identity law. Okay, for the sake of the laws, okay, and then this one is called a negation law, okay, and then this one is called the discrete kind of things. Okay, discrete. Okay, okay. So I observe this, then I combine the terms here, right? So I'm left with RC or PC. And then this one, I turn it back to the implication. Okay. And then since this C we work with is general, so any C works. And then I use universal general. Okay. Yeah. Any question from the others? Any question from the others? Please don't afraid to ask. Encourage you to ask in the class. Any other question? Any other question? Okay. If not, then we go to today's lecture. So okay. So last week we mentioned about subset. Did we talk about equality last week? Yes or no? I forgot because some classes taught until this part already. I'm not sure this class had taught about until this part. Have we talked about this subset last week? Subset. Yes or no? Yes. Equality? Not yet. Yes. Yes. Okay. Then maybe proper. Okay. So last week we talked about the subset. What does it mean for a set to be a subset of the other set? So for every x here, you need to show that that element is in the other set. Okay. So when are they equal? A and B are equal if and only if A is a subset of B and B is a subset of A. Okay. This is a bit like the less than equal to or greater equal to. Okay, and then the other concept I want to introduce is a proper subset. Okay. So what's a proper subset? Okay. So a proper subset is A is a proper subset of B if A is a subset of B but A not equal to B. That means there's some element in B that's not in A. Okay. I think last time I draw some pictures, something like this. So the clock number is a proper subset of n, right? Because for example, 13 is not in here. And then, for example, natural number is a subset, proper subset of the integers. For example, -1 is not in here, right? And then the integer is a proper subset of the rational. For example, half in the rational is not in the integer, okay? And then also the rational is a proper subset of real numbers, and then real numbers is a proper subset of complex number. And then this is maybe some how they sit inside here, right? Okay. So you can see that if you look at, for example, the okay, this you can look at it as a complex number. So complex number is a R2. So you can't feel a single R can't feel the can't fill in the spaces, all the spaces. So it's a proper subset. And then last week, I think one of your classmates asked me, so what is a proper subset of an empty set? Right. You can try and prove that actually the proper subset. So this is like left as an exercise. Okay? So exercise. So prove that prove that proper subset of an empty set is an empty set. Okay. Yeah, try and prove yourself just using the definition we did in the class. What's a proper subset of an empty set? Okay. Next. Okay. So last time we mentioned about how big is a set is, how small is a set is, right? So today we'll talk about this concept here. So this is called the cardinality. Okay. So the cardinality of x is the number of distinct element in x. Okay, denoted by modulus x. Okay, so if the number of distinct element in x is a finite number, n, then the modulus n is equal to n, and s is for a finite set. Okay. Otherwise, the set x is whole infinite. Okay. Okay. So for example, what's the cardinality of the clock number? Oh, okay. Thank you. Okay. If I If you forgot what's the code number, it's like 1, 2, dot 2. Okay. And then how about the cardinality of the empty set? What's the cardinality of the empty set? 0. Okay. So yeah, so the code number and set. Finite. Okay. What is something not finite? For example, infinite. For example, and then let me see. Okay. So yeah. Okay. Okay. Maybe we won't touch on in this course, but you might be able to see that you can't see it, but maybe you can read somewhere that the cardinality of n is equal to that equal to about this. Yes. Okay. But they are less than the real number. Okay. But this one is the level of infinity. Maybe not touch on this course. We will see how it goes. This one is just extra. Okay, next. So given a set, we also can study the proper set. The power set. Okay. So what's the power set? Oh, see. So power set of X is a set. Okay, first of all, a power set is a set. Yeah. Set consisting of what? Consisting of all subset. Yeah. Set X. So it's denoted by TX. Okay. For example, so we got this set here 0, 1, 2, 0, 1, 2. Okay. So what are the subset inside? Okay. Remember that we proved a theorem that every set contain what? Contain a empty set and the set itself. Okay. First of all, the empty set. The second, the whole set. Okay. What are the subset inside X? Okay, let's see this X. 0. So what are the set that is contained X? Okay. What kind of subset you can build? For example, the set containing 0. Okay. The set containing 1. Right. Right. So like 0 is a subset of 0. Correct? Okay. Because every element here is an element here. Okay. And then similarly we have 2. And then we will have 0, 1, 0, 2, and 2. Okay. That's all. This case. Okay. So this is a power set. So power set study all the subset inside the original set. Okay. And next. So next we want to talk about we want to multiply products. Okay, we want to study a product of two sets. Okay, before we discuss about the product of two sets, we need to introduce this notation first to describe the element inside your product. So we define this ordered n tuple. Okay. So this is not too unfamiliar to you. It's like the xy coordinate, but this one is an extension of it. So it's the ordered collection. Okay, that and then A2, A3, so on. Okay, up to AN. Okay. So you order the element inside your set. The second is the this one, the N element. Okay. Yeah. So for example, when okay, let me write here better to refer. So when n equals to 2, these are called the pairs. Okay. Okay. So for example, A1, A2 might be different from A2, A1, right? For example, the point 1, 2 is not equal to the point 2, right? In the so for example, like 1, 2, and then 1. Yeah, these are two different points. And so the order is very important. So that's why we call it ordered pair, ordered connection. Okay. So why we want to talk about this? Because we want to take product between two sets. Okay. So let's given two sets. Okay. The product we're gonna introduce is called the Cartesian product. So the Cartesian product of A and B. Okay. Or sometimes we wrote A times B. Okay. Is the set. Okay. So the product of two set is still a set, right? So a product of two numbers is still a number. Okay. It's a set of what? So what's the element in there? So it's a set of all ordered pairs. Okay, look like this. Maybe. Okay. The first one is in the first coordinate, and then the other one is in the second coordinate. So we can write it in the set notation, which is A, comma B, where A in A and B in B. So sometimes you'll notice that I will put a colon here. Sometimes I don't put colon here. So when I put colon and I put a equal sign, this means I'm defining it. Okay. If I don't put column here, this means just equal. When I put column, I mean defining. So this is the first time I define this notation here, A equals B. So I define it. Okay. So for example, what do you have? So let's cross this two set here. What do you get? What do you get? 1, 2, 1, 3, 2, 2, and 2, 3. Okay. Actually, you should be familiar with this. This is if you remember the high school map, the R cross R. So every time you draw the graph, right? So it's a R2. Okay, later we'll touch on it again. So in general, not here. No. In general, A cross B is not B cross A. Okay. So you can try with this example here. Try the exercise. So try show that B cross A is not equal to A cross B. Okay. Okay, so generalizing, so since we just now introduced the n tuple, right? So you can try you can try yourself, define what is A1 plus A2 plus A3 up to AN. Okay. Try define yourself where AI. Okay. Okay, any question up to now? Any question? No? Okay, next. So next. So this one should become earlier, but we give it in the back. So let's do this. So let's be given a predicate and a domain. Okay. So this is the second way we write how to give the set notation. So this is, we just try to make it precise here. So a truth set. So every time you see me writing the slash, the condition here, so we're trying to make it precise in this definition here. So the set of elements X in D. So okay. So what am I defining here is the truth set of X. Okay, so what am I trying to emphasize here is you need to specify your domain always. Okay, always specify your domain so you talk about the element here. So for example, I do it here, right? So so this one specified where is the A is and the B in. Okay. Every time you need to say where the variable in. Okay. For example, I can have the same predicate but different answer. Okay. So consider this equation here, algebra equation here, but I consider it in a different domain. So they result in a different set. Anyone like tell me what's the element in example one? What number satisfy x to alpha equals to 1 in n? 1. Anything else? Negative 1? But negative 1 is not in n. So it's just 1 in this case. Yeah, I think we can add another one. So maybe 2, 3, 3, 4. So if I go to Z, what do I have? Okay, maybe I name them. So let's call them A, B, C, D. Okay. So A is 1. So B, just now we somehow say -1, right? -1. How about C? What do you have? 1, -1. Anything else? Anything else? No? Okay. Okay. How about D? What's the number that take power 4 to 1? Okay, I think 1 also got, right? Because subset. -1 also got because subset of C, so definitely I. Okay, I. Any more? Any more? No more? You sure? Huh? -5? Yeah, -5. Okay. So this is called the root of unity. So you can see that same predicate, okay? Same predicate. I didn't change the predicate. You see? I didn't change the predicate. But I changed the domain. And the set can be different. Okay. B equal to C, but A doesn't equal to B, C doesn't equal to D. Okay. So they can result in different set. Okay. These are different set, although the predicate are the same. Okay. Root of unity. So degree, the roots, the number of roots should have the same number of degree. Okay, this is a fundamental theorem of algebra. Okay, next. So now we can multiply. Let's go on again. So okay. So next we know how to equal two set. What does it mean to be two set be equal? And then the cardinality, okay, how to count element inside for finite and infinite. And we also know how to take products between sets. Now we want to take an operation called union. Okay, so we want to take union of two sets. So maybe I just use, okay, so let's carry on. The union of A and B, okay, we write as A, this one is a cup, cup B is a cup. Okay. So this is defined to be the element that is either in A or in B. See, so here is a cup. Okay, here is the or in your predicate logic. Okay, so is a sentence. So these are contain elements that are either in A or in B. Okay, or in both. Okay, for example, 1, 3, 5 union 1, 2, 3, 5 is equal to what? One, two, 1, 2, 5, 1, 2, 3, 5. Okay, 1, 2, 3, 5. If you take, okay, think about the multi-set first. How about this? Oh, shit, I write the answer out. So R union the natural number is what? Actually, it's not the answer. Wrote the wrong one in my notes. So R union N is what? Yeah. Okay. So be aware of this equality here, right? So this is something non-trivial. Okay. You need to show this equality. Remember how to show? So we have to show the two subset, right? Right. So we define two set to be equal if the other is so they are the subset of each other. Okay. So similarly for here, you need to show the subset of each other. Make sure you know how to show. Okay. You need to show whenever I ask for set equality, right? You need to show this set using this set inclusion. Okay. You know how to show? So I need to take an element here. Okay. Need to show that it's in here. So for example, okay, maybe we'll do an example. Okay, this one is very important. We need to show set equality. So okay, let's do it for this case. Okay, so I need to show this. You need to take an arbitrary take an arbitrary element in R U N. Okay, so S is in R or X is in N. Right, this one is by definition, right? Remember by definition. Okay. Right. So can you show that S is in R? Okay. Can you show why? Because if okay, so either X is in R or S is in N. Okay. So but remember that we have a set equality inclusion that N is a subset of R. Right? No, okay, no. Okay. X is in N is also in R. So in this case, it's so how do I put it? Hence, right. If X is so all statement, right? All statement. When is the all statement true? Either one of them is true, or both of them is true, right? So if this one true, it's in R. If this is true, N is also a subset of R, so S is automatically in R. Right. So this one, the not here is like by the lecture example. Yeah. Okay. So it's in R. So you show that when you take an arbitrary element here, you show that it's in R. Right. So the other way around, how? So the other way around should be easier. So show R is a subset of R union N. Okay. Take X in R. Okay. Then X is in R or X is in N. Okay. This is the predicate logic. Remember the addition law just now we touched on in the start of the class. So you have one statement that is true, you can take it disjunction with any statement. Just now we did in the start of the class. So you can take this, then finally got x is in R. Okay. So in general, every time you see this set inclusion here, make sure you know how to go from one set inclusion and then to the other set inclusion. Okay. Make sure you know how to do this. One last example here before we go to the next concept. So the last example here is, let's look at this union here and try and figure out what's this is. So let's take the union of intervals, closed intervals minus n and n. Okay, first let us take the finite one up to n. What do you think this is? Okay, I'll let you think first and then write out the infinite one. Recall what is the definition of the interval is. So these are the elements in where? In R, such that what's the predicate? The predicate is x is in between B and A. Since this is closed, we need to include A and B. Okay. So any idea on the finite union of the interval? Minus n n. So yeah, okay. Any idea? Oh, do you understand this notation here? So this I here, right, is meant to be going, I here is in the uh, okay, natural number in this case. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9. Until one number n. Any idea on this one? Yeah. Any guess? No? Okay. Maybe we take a break and then we come back and we'll discuss.
这个是你刚上课之前上的那个呀，有点
嗯
就是从也是这儿，
嗯哼
哦，我记得这个
，OK，
是这怎么的，就是从这一步怎么到这个，
哦，你能不能从这步到这步？这步
哦，我是这样子的，我是把这个变成这个，成这个，没问题的。
那怎么来呢？哦
就是把这个跟这个，这个跟这个，啊不对，这
哦
个跟那个，这个
哦，
跟那个。
可以，你把它变长了。
对
，OK，好。
但是我发现，那这个东西不就是 Q 吗？
Q Q O P，为什么？为什么这个？
这个不是
不是啊，因为它这个是 N 和 O 啊，不是 O 啊。哎，也不是 N，为什么是？你说这
啊，对，
整个嘛变
一整
Q
个，
嘛？
对，
哦，你是用那个什么，是不是？那个排列，对不对？
我记得是只要它们两个符号不一样，然后三个字母有两个一样的话，就找那个一样的。
哦，好像是，好像有，像有。对对对对，OK，
对，
好，
那是这个。
哎，
那么这个往下来的话，等于一个 Q 还是 Q？
可是这一个就不一样了，因为这是减 P 嘛，这是 P 嘛，这是 Q 嘛，它不是 QQP 还是 PPQ 嘛，对不对？
我知道，
但是
真的下来是 Q。
它下来是 Q，为什么？
可以用那个针指，就是那个你可以找一下它那个针指表，看好像就是咱们之前好像讲过这个。
正过吗？
我正过。
你正过？还在吗？在这个表上面有的。看一下，OK，我觉得我知道怎么正，你有笔吗？哦，
其实就一样的。
哎，这是我在班上写的，
对啊，那
好像我在班上写的有问题，但是我在这里改了。它好像它不是 logical equivalent，但是它是一个，如果这一个引牌就是一个 tautology，但是它不是一个 logical equivalent
哦，
啊，
这不是一个那个
它不是，
逻辑。
对对对，但是呢，但是这一个 imply 那个是 tautology，知道怎么说？
没有。
就是如果这一个 imply 这个
嗯，
是一个 tautology，但是这一个不是一个 equivalent，
那这个
了
怎么
解，
这个？
这个就不行。哦，OK，这个这个感觉好像有一个方法，说再把它拆掉。
拆开吗？
嗯，对
那就非 P 或 Q，然后和非 P 是不是
，OK，你是哪一个？应该有诶，没事，我有记录，我有记录。哎，对对，OK，对，
非 P？
没，OK，这是合 P 嘛，对不对？
对，和
然后
P。
这一个是一个 contradiction，所以这个 false，
这个是 false。
所以这个 false 和这个，所以剩下这个嘛，对不对？
对。
对吧？
是 B 为真。
哎，所以你又回去上面了，
啊，
回去上面 Q or not P and Q，对吗？
哪个回去了
这个
？Q。
这是你啊，
这个它最后出来成什么了？
这个
因为它是真的，所以说左边必是。
这个和这个，
对，
所以这个和这个有什么？
这个就出来
来回去他自己，回去这一个，
就还是自己。
对，还是这个，所以这一个等于这个，对吧？
对，还是等于这个
然后这个就变成这一个
等于 Q。或 Q，或 Q，
什么后面
就把这个 Q 拉到。
啊，没有啊，变成这个，
哦，对，
这个，
那最后它出来的用号码删掉了。
删掉，不会，
删掉了。
在这里这里，然后
那这个东西出来等于什么？
这个东西，
它没有再往下化点了，意义，对吧？它没法再往下化点了。
对啊，对啊，对啊，没有啊，没有，没有，这个就是我们要的东西嘛，对不对？
嗯，OK。
我问一下，就是 this character equal to
complex，
实数 plus 虚数，是这个意思。我在
对，
中国没有见过这个。
哦，这个是 complex，就是虚数，哎，虚数嘛，就是叫虚数嘛，
只有虚数，没有
对对对对
没有实数，就 R。
R 是在 R 是在 C 里面，
R 是全体实数。
全体什么
实数就是
啊？
一跟二都算实数。
对对对对对对对对对
然后 C
对。
就是实数加虚数，是这个意思。
但是我想说的是虚数里面包括实数，
虚数的
虚数是什么
I 嘛，
？I 不只有 I 吗？那 A 加 BI 叫什么数呢？
也叫
也叫虚数嘛，对不对？所以
就
实
C
数包在里面。
哦，C 就是实数的意思。
Yes yes。你刚来，你是不是刚？
没有
哦，你没有，你上周也来。
来了。
OK OK，我还以为你是 Visa，我不知道有人好像是 Visa 不能说啊。
上个礼拜的那个 tutorial，这个
啊，那个礼拜读多少？
还是挺。
你为什么刚才不要问？
因为上课啊，我在问就不要上课。 没有问题。对，你是讲第3个 step 跟第5个 step 错？
Yes，
为什么？
因为不能够 imply PC 或者 QC，
所以要改成你
什么要改成不能改，这个 proof 不能改，
所以
这 proof 不能用，
所以这个想 proof 对，要 proof 这个
不能 proof 错的。
错的。
因为我们上次有一个 tutorial 已经说过一个 content example。From the average of 3 classes, right? With average from 8 classes, I think DMT got the highest for quiz 1. So please keep up your good work. Yeah. 2 more weeks we will have another quiz from Seng. Okay. Does anyone have any idea? What's the finite union of this minus I and I intermediate? What do you get? What's the set you get? Huh? Tell what? Tell me, teacher. What do you mean? What do you mean? All integer over there? What do you mean? You mean like this? No. No. You know why? Because, for example, 0.5 is in here, right? But 0.5 is not in here. Okay. This is the basic check. So this is not. Okay. Anyone want to try? Minus n, and then n, and then close interval. Okay. Yeah. Okay. Of course, when I say like this is non-trivial, you need to show me that use this method here. Okay. Exercise of show me that these two sets are equivalent. Okay. Show this equality here. Because I already defined the set here, right? So using here. Okay. This is the definition here. Okay. This one is the union. Okay. I also define union for you. Okay. Either on this set or on this set. Okay. So you need to produce this proof here to show this equality. Okay. Okay. How about this one? How about if you take infinite union? What do you get? You get infinite union of this minus I equal. What do you get? Who? R? Okay, R. Yeah, the answer is R. So I need to show. Okay. So one thing I want to warn you is okay, this is a bit hard to show, but yeah. But what I want to say is like infinity is not in here. Okay? There's no infinity. There's no number called infinity. Okay. Okay, next. So we define union. Now we want to define intersection. Okay. So union, we just take any element with A and that is inside A and B or B. Okay. The intersection we want to take is only when they both have the same element. So it's denoted by A. This now is cup. Now it's cap. Okay. This cap. B. Okay. Is the set meaning element in both A and B. Okay. So A in B. So we write X is in A and X is. Okay. So similarly, okay, I forgot just now. This one you should also be able to generalize the definition to like you can take a finite intersection or infinite intersection. Okay. Okay. So similarly, you can do it for this union here. So generalize to A1 union A2. Finite union. Okay, I give the name finite union. So up to AN. Up to N. AI. And then all the infinite union. A1, A2, forever. Okay, not that I got the index set here. So this number here, right, I can change one. So I can change to maybe J, use J. That's fine. Okay. As long as you know where you are starting with, and where you are ending with. Okay. The index set here is you can use any alphabet. Okay. So how I define this is exactly what I wrote here. So I should put a dot here. Okay, this is how I define. Put a colon here. Colon and a equal sign. So how I define this is exactly this. How I define this is exactly this. This is the notation. Okay, next. Come back to this one. So let's see. Let's see. Okay. So e.g. So let's see. What is this? Intersect this. What do you get? What's the intersection of these two sets? 1 and 3. Okay, good. Next one. How about this one with this one? Real number and the natural number. You get natural number. Similarly, you need to in your mind, right? When you see this set equality, you need to go through the set inclusion. Okay. So why is this? And then why is this? Okay. You have to go through the whole process, okay, in your mind. I will ask you to prove some tests. Okay. Okay, so let's see. How about this one? Okay, let's look at this. Take the intersection of 1 over n. Okay, let's look at this. I like it. What do you think? Okay, maybe you think first. Let me write out the fourth one. Let me write out the infinite intersection of the. Okay, now I give you 2 minutes to think about these two questions. You can discuss with your friend and see what answer you get. Infinite intersection and the finite intersection. Okay. 1 more minute. Think first. Okay. Any idea? Any idea? Question. Example 3. Any idea? Any idea? Okay. This one is negative 1 over n to 1 over n. Okay. So since this is a set equalities, you need to take every x here and make sure that it's a x in here. And then take every x here, show that the x is in here. How about 4? What do you get? Huh? This is not 0. Huh? What? 0? Is it correct to write like this? Huh? Set containing 0. Okay. Yeah. Okay. Okay. So yeah. So actually, yeah, there's a nice structure here. You see, if you take union of intervals, you still stay with intervals. But if you take intersection, some things can go wrong when you take infinite intersection. Okay. This is some features that are capturing this real number here. Okay. So once you take so intersection doesn't behave well in real numbers. So you can see some structure here. Yeah. So yeah. So if you like maths, you can do a topology class from this. Yeah. This is some structure on the real number. Okay, next. So next. So we said that two sets are disjoint in the section is empty. Okay, why I suddenly jump out with this definition here? So we've got a theorem here. Maybe I don't want to prove this, but you should be able to think about it. So let's see this theorem. I think this theorem is also taught in your school. Maybe you just calculate it. But now I want you to think of it as the way we learn today. So what this translates into is the cardinality, okay, of the union of two sets is the sum of the cardinality of the two sets respectively and take away minus the intersection, the cardinality of the intersection. Okay. If they are disjoint, right? If they are disjoint, then this part is just 0. Okay. So A union B is just A plus B. Okay. But when they have intersection, you need to take away the intersection. Because when you do this sum, you will count the intersection twice. Right? Can you imagine? We won't prove this in class, but you need to know how to think of it. If not, maybe you ask me the next lecture, or if we got time later. Okay. So, I mean, this one is a simple statement that you should know. Okay. Okay. Next is the difference. So we have two sets. We also can look at the difference between them. Okay, so I put this as an exercise proof. Prove it. Prove it. Okay, and then so the difference. Okay, the difference. Wait. Difference A and B. Actually, the order here is quite important. So let's see. Should I say A? Okay, maybe A by B. I don't want to say A and B. N is like you can commute. So I just put A by B. So I name it A by B. So A by B is like A take away B. Is the set. Maybe elements that are in A but not in B. Okay. Or sometimes we wrote A slash B. Okay, slash B. So it's defined by X such that X in A and X is not in B. Okay. If I really want to be pedantic, so I need to write X in A and then X in A and X. Right. So if I really pedantic, I say that I need to say that this where this X lies, right? So I can write in this way. Okay. So you should try this. Try this with all the previous definitions I wrote. You need to mention where this X lives first, and then you talk about predicates. If you really pedantic, okay. And then, okay, for example, let's try the two set again. What do you get if you take the difference of these two sets? 5. 5. 5. This 5. Set containing 5. Okay. And just make it 5. But you should note that, okay, A minus B in general. A minus B is not equal to B minus A. Right. So in this example, you can see that if I take 1, 2, 3, take away 1, 3, 5, what do you get? Set containing. Okay. In general, they are not the same. Okay. It's not like you. Yeah, even in numbers, it's different, right? So for example, like 2 minus 3, 3 minus 2 is different. 1 is minus 1, 1 is 1. Okay. Yeah. Okay, next. Okay, next come to this universal set. That time Danzo asked me about this. Okay, yeah, universal set. So I think there's no universal. Okay, never mind. I don't want to talk about the thing first. So, and universal set is the set meaning yeah. How to remind you about this universal set? Later, I'll show you the Venn diagram. Then you will remember what's the U thing. Okay. So for now, let U be the universal set. Yeah. And then we want actually this universal set you want to talk about a set living in another set. So it's like subset of another set. So you can think of it. Universal set is the mother, not mother. Maybe something bigger that containing the set you want to study. So if you want to take away the small set, then we will consider the complement, the thing that left over. So the complement of the set A. And we will denote it by A bar. A bar. Okay. Is the complement. And now this complement is an English complement of A with respect to U. Okay. Sometimes, right? Sometimes I think I usually write AC, okay, A complement, A complement. Or sometimes you will see some people say A slash U slash M. You take away M to uh to emphasize what's the universal set. Okay. So sometimes you will write like this in U such that X is not U. Okay, good. Then next. So let's see this example here. Suppose our universal set is a real line. Okay, remember I draw the line for you to see. Let's say I take away this guy here. Take away -1 to negative infinity and 1 to infinity. So what do you get? What do you get? Do you think? -1 to 1? Closed interval or open interval? Close. Both sides? Yeah. Okay. So the number that I don't take away is -1, 1, because it doesn't include in A. And then also the things that in between them. Okay. So in a geometry, you can see like this. So -1 to 1, and then this one, and then this one, okay, this one. Okay, and then here, it's what you have. Okay, yeah, yeah. Sometimes in the space, sometimes we don't study. We want to study the complement of the space. Okay. Yeah. Okay, never mind. Next. So, okay, I got some Venn diagram representation here. So I think maybe you are quite familiar with this, I guess. So I have two sets here. Okay. They for now I let them intersect. And then the set that contain all the set that we consider is called the universal set. That's why I have a U here. Okay. I got six kind of shaded different types of shaded regions. So These shaded regions all represent one kind of operation. Okay. Maybe spend another 2 minutes and then try and figure out what each picture representing. You can discuss with your friends as well. I'm not sure, but maybe there are more than one way to write for one diagram. Maybe yes, maybe not. Not just one way to write it. Forget to pass down the presentation. Okay, let's try. So first one, what do you have? Okay, let me write down the numbers. Otherwise. Okay, first one, what do you think? Huh? What's the operation? Intersection. Okay. A intersect B. Anyone wrote B intersect A? Huh? Yeah. Okay. Yeah, it's the same. Okay. How about 2? A union B. Anyone wrote B union A? Yeah, same. Okay. How about 3? How about 3? U minus A. Okay, I think this one is a clean answer. Any other answer? Huh? Say again? Complement of A is same. Okay, it's a different way of writing only. This one is the same, it's different way of writing. Complement of A, U minus A. No other answer? I don't know, I never try, I haven't tried. Okay, if you have other answer, you should try, tell me, and then how about 4? A minus B. A minus B? Okay. Yeah. Any other answer? If you have, you should shout out. How about 5? A minus B? A minus B plus B minus A minus plus. Wow, you already turned union into plus. Okay. Any other answer? I think this one got more answer. Huh? A union B minus the intersection. Huh? Okay. Okay. Oh, okay. Any more? Okay. Maybe leave it here first. If you have answer, you should tell it out. And then we should check. And then how about 6? Huh? Say again. Union of A and B, and then take the complement. Okay. Any other answer or not? I think I also can take AC intercept EC. Okay. Do you see something like the Morgan's law happening here? Yeah, this is how I guess it. Okay, any other answer? No? Yes, in fact, we have this set identities here, similar to the table we have before, right? So we have these identities laws, okay? Then you can think of it as the false true thing, right? Okay, domination laws, idempotence law, remember? Square to 1, square to pixel. And then this one is the double negation, right? If it is in the logic. So here called the complementation law. And then commutativity law. And then associativity laws. Okay, distributivity laws. De Morgan's law. Absorption law. Okay, I think this absorption law, right? In set theory is easier to understand than the logic. If you think of the set theory, right? Complement law, yeah, remember the P and not P negation. Okay, so they have two operations here, union and intersection. Okay, in logic you have the N and O, N and O. So two operations with these identities. Actually, they are examples of one algebra called the Boolean algebra. So Boolean algebra is the last topic we will touch on in this course. Okay. So by now you should be very familiar already as they keep popping out these laws. Okay, anyways. So you should also prove it, right? Prove it. Last time, how we prove is using the logical equivalence, but now it's using the set equivalence. Okay. You should be able to prove all of this using the definition. Okay, this is an exercise. So exercise. Someone in the Teams asked me, teacher, I finished the tutorial question. What should I do? I say you should do the odd number counterpart and then finish all the question inside the book. If you could finish that, you can finish all the reference, the question in the reference I put in the folder. Okay. And also you should try to prove all these, right? Prove all these identities. Okay. Okay, I will show one in this class. I will show one in this class. So let's show this. So the complement of A union B is a complement of A intersect complement of B. This one is what I wrote just now. Okay. There are two ways to prove it. One is the classic way. Okay. So the classic way is what we did just now. So we need to show the two subset inclusion. So first, show that A union B is a subset of the complement B. Okay. And then, so we need to take any x in A. Okay. What do we have? We have x is not in A union B. Right? Okay. Is this how I define it? Let's see. So, yeah, see? So if x is in here, that means x is not in A. Okay, by definition. So always go back to the definition. So if x is not in A or B, that means So you turn into the sentences. It is not the case that X is in A or B, or X is not in A or X is not in B. Okay. And then from here is the predicate logic, right? The De Morgan's law. So, okay, I think I should write it out, otherwise you confuse. So this one is the by definition. Okay, by definition. This one is how to say? Translate into English. Translate into predicate logic. Okay. Okay. The next one is also translate into. Oh no, this one is by definition. So you see, by definition, we turn into predicate logic. Okay? The all, the set all here become a all in the sentence or in the statement. And then next you can use the De Morgan's law. So now you can use this De Morgan's law. Okay. So here is the De Morgan. Okay, to be precise, this is a De Morgan's law for predicate logic. Okay, since now we have a set theory, also have De Morgan's law. This one is for predicate logic. Okay. This implies that X is not in A and X is not in B. Okay. So this one is what? This one is just by definition. And that implies what? X is in the complement of A and X is always in the complement of B. So this one, so you show that. So you show that X is in A intersect B. Okay. Yeah. Okay. So we get X in. Okay, so we get A, the complement of A union B is the subset of A intersect B. Complement of A intersect B. Okay. Okay. Any question about this? Any question? No? Yep. Yep. The first, this one first. 4. 1, 2, 3, 4. This one. Okay. How about it? Yeah, yeah. What about this fourth one? Huh? What? What? What do you want to ask? You haven't asked the question. The fourth one, what happened? What happened to this one? How to get this? Oh, how to get this? Okay. Yeah. So how to get this is okay. So this is the negation, right? So yeah, let me write down the English maybe. So it is not the X in A or X in B. Right. So you are negating an or statement, right? So this is like, okay, I turn it back to the logic again. So not P or Q. What do you get? You get not P and not Q. So the fourth one is not P and not Q. Okay? Are you following? Are you following? You okay or not? Can you understand? Cannot. Huh? What? What? Cannot hear. Huh? You think of it. Okay. Okay, I let you think of it. If you can't get it, then you ask again. Then you ask again later, okay? Follow up. Okay. You go hospital, you also need follow up, right? Okay. See? Okay. Okay. This one is practical logic. Okay. Okay, actually haven't done, right? So that's the second part. Second part, I leave it as an exercise, okay? So, repeat the step. Show that A in the other way, okay? The other set inclusion, okay? Mm. Okay, next. Next. Actually, there's another method here. This method will remind you of this truth and false table. And then what is it? The Boolean variables. Actually, you also can use this membership table here, but I prefer the set inclusion. Maybe I'll mention in the test I want which one of which kind of proof. Okay, so why do we have this membership table here, or how do we use it? So we list out all the possibility of the element. So the element can be both in A and B, which means they are in the intersection, or they are maybe in A but not in B, or they are in A but not in B, or they are not in A, not in B, right? So this is like, okay, if I draw these two out, let us see where's the tuple is. So 1, 1 stay here. Okay, let me label A first. 1, 0 stay here. 0, 1 stay here. 0, 0 stay outside. Okay, so we look at all the elements. Okay, we analyze all the elements at once. So next. So if it is not in A, then it's not in A, not in A, become in A. Then not in B. Like this. Okay. So A union B. So how you interpret A union B here? So if something is in A, something is in B, of course it is in A union B. If something is in A, something is not in B, it still in A union B. Okay, because A union B, the definition is either in A or in B. So similarly, you get 1 here and then get 0 here. Okay. If you want to look at the thing outside, you'll get 0, 0, 0, 1. Okay. And then how about this one intersection here? So if you have nothing in the complement, you have nothing in the B, in the other complement, of course you got nothing inside the intersection. Okay. If you have something in the complement of A, but something in the complement of, okay, this one is this case. If something in the complement of A, but nothing in the complement of B, so they have no similarity, right? Similarly for this, if you only have element in complement of B, don't have element in complement of A, you also have nothing in common. So you get 0, 0. Okay. And you have something in A and then something in B, then they have something in common. So okay. So this one represent one element, okay? So I should say one represent and non-repeat. And Okay. So things, you see, this element mesh up. So by definition, no, by definition, these two have the same element. Okay. You found the element here, it's also here. It's not here, then not here, not here, not here, not here. Okay. Okay. But I prefer the set inclusion. So you should learn the set inclusion. Okay, yeah. Next. So next we talk about this multi-set here. So I think multi-set is important for you guys, so I'll do it. The multi-set is okay. Last time we said that there must be distinct objects, right? But here no need. Here just any elements, okay? But elements can appear more than one time, okay? An element can occur as a member more than once, okay? More than once. For example, we can get one, 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 two, two, three. Okay, this is a proper set, proper multi-set. Okay, if I put like one, two, 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 three, then they are not the same. Okay, this the idea of subset is still the same. Okay, must be found one in here and then the other must be the other. So in this case, right, we have the new terminology called multiplicity. So since they appear so many times, right, more than one, right? So we want to like quantify the number. So we call it multiplicity. That multiplicities. Okay, for example, what is the multiplicity of one in this set? One. What's the multiplicity of one? 4. Yes, 4. Okay, multiplicity of 2? 2, right? 2. Okay, multiplicity of 3? 1. Okay. So in this case, you can think that the cardinality of the set is the sum of cardinality of the set is actually how to define? What do you think? Is the sum of is defined to be the sum of the multiplicity. Okay. So elements here should be this thing. So the multiplicity of, for example, just now is 1, 2, 3. What's the multiplicity of this set? Is 4 plus 2 plus 1, which is 7. Okay. So the idea of subset, okay, you should, so because we just defined the subset for set, right? So you should be, you can define similar, okay, let me write it properly. So define similar concept, try define similar concept of subset. Okay, I think that's all. The other one is union intersection here. These are a bit different, so I list it out here. So if it is union, right? This one a bit different. If it is union, right, you don't just take all of them. Okay, you take the maximum of the multiplicities of the element. Okay. I'll show you in example later. And the intersection, you take the minimum of the multiplicities in two sets. And then the difference is it's different also. You have to take okay, take the difference of multiplicity in P and Q. And then the sum you take the sum. Okay, let's see in the example. Okay, let's see in the example. Okay. So so in A union B, you take the maximum of the multiplicity appearing in A and B. So for example, 1 appears 4 times here. And then B, 1 appears 2 times in B. Okay, so this is the max of these two. And then how about 2? The max of 2 and 4. Max of 1 and 2. Okay. So you get 4, 1 here. So you get 1, 2, 3, 4. And then you get 4, 4 as well. 4, 2 as well. And then 2, 2. Okay. So it's not like taking all of them, right? So if all of them is like 6 of them, 6, 6, 6. Actually, this is the concept of sum here. So the concept of sum here is taking the sum of them. So don't confuse with the union and the sum in the multiset. Okay. So if you want to take the naive union, it's actually the sum. Okay. And then the intersection is what? Intersection is the minimum of the number. Okay. It's then this and then this. Okay. So it's like 2 of 1 and then 2 of 2 and then 1 of 3. Okay. And then the next one is so this one is you take the maximum of the first one appearing multiplicity of appearing in the first one and then take away the second one. Okay. If this is less than 0, we just take 0. For example, in this case, we'll have -2, so we will take 0 in this case. Because you can't have negative elements inside the set, right? So this one is 1 minus 2. Yeah. So you get how many? You get 4, 1, 2, 3, 4. 2, sorry. 4 minus 2 is 2. And then 2 minus 4 is -2. So you can't get -2, 2, right? You can't draw negative thing. So you get 0, 2, and then you get 0, 3 as well. Okay. Okay, let's look at this picture here. So A, take away B. So this one take away. Okay. But you need to take away 4 of them. You only got 2, so all of them have to be gone. And then 1, 3 here, and then 2, 3 here. So all the 3 have to be gone. So you're left with 2, 1. Okay. 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 In that case, we leave the function and matrices to next week. Okay, we will break into the break, and then can row by row come and pick up your quiz, and then because I want to keep a copy, so once you get the quiz, you can study it, and then can you take a photo of it and then bring back? Then you don't need to bring the paper back, and then you after the class you give me back the paper, and you just take a photo, and then this quiz will be with you for 1 hour. Okay, can row by row come and take so that it's not messy. Maybe first row, and then the other can go for rest and then come and collect later. Can first row come and collect your quiz first? Too many, yes, maybe break into so you can find your name. Where to sort. 呀，没有到。OK。哎，下次我开课你可以盯住我的。多少钱啊？
这个是 LT 或者是一个什么意思？
就是它出现的次数。
这个会这样问？我抄一下。
因为不然我们不知道怎么说呀，就那个次数。Level 3。Where do you sit? You saw level 3? Oh my god. Yeah? Huh? 杨月涵 not back yet. Yeah, but let me see. 哎，为什么谁传错去？绑一下，绑一下。来，done。7 OK。Em.没错，没错，这个也是错了，这也错了，都错，都错。但是如果它这个是对不对？OK，不要读，OK，没事，这错就这样，错就这样，错就这样。我怎么说呢？
这个是你的，这个是你的。
你怎么理解它？
然后
对你来说啊。 啊，但是你有爱你也可以是的，也可以是的。啊，只要是一条那个，只要是一条，有我跟你说，啊，是一条。OK，你先看原本啊，它是有复数这一个，然后每个数之间都有一个数，会知道。然后一种想法可以把这条线想成它，或者把这条线想成它，或者把这条一种方法是你可以转它，对，转成原本这条，嗯，我这只是给你一个想法吧，但是我没有具体告诉你他们为什么这个是 R，这个是 R，这个也是 R，但是我只给你一个想法吧。但是现在我如果要告诉你为什么它是，对不对？其中一个想法你可以想的是，如果你去转动它，OK，等一下不是之后我们会学一个东西叫做方向，就是你去可以有一种哎，就是去转动它，能够想象吗？转动是？不能想，比如说你看很容易想啊，这条线转动它，变成它，这条线转动它，变成它。啊，这条线还有一个想法，我也还没有教，因为是方程，所以如果你能够把这里所有的东西都送去这里的话，或者你可以证明，因为这两个是 set 嘛，两个 set，如果你一个方法从这个 set 说的每一个在这边的东西都是一个在这边的东西，每一个在这边的东西都是在这边的东西，这样他们就是对，对，没错，没错，没错，没有错，没有错。但是我是没有教你怎么理解，我只是给你一个想法的。我画这张图的时候都拿了。呀对，那个东西它可以帮你搞懂，什么意思？哦，OK 哈，我也不确定现目前，现在把它然后对，是只是说怎么想哈，比如说给你这两句，你怎么想这句哈？不一定，我也不知道，可能会，可能。OK，等一下，OK，no，
不好意思，我背叛了。
OK，哎，6:05，哎，6:02 already 哦。Is everyone back yet? Everyone signed the attendance list already? Everyone signed yet? Why this line got this one? Okay, I think should be back, everyone. I think rest time already over. Okay, so let's discuss this solution. Solution. By the way, if you have any question on the marking, you should find me directly, maybe after class. Okay, so the last advice I give you in the exam is actually this restaurant is not important. Okay, it's just a logic question. But what I expect from you is when you say it's not a proposition, you can say that it's a question. This is what we did in the prior question. And some of you said that it has no true values. Okay, it is not true or false. Okay, cannot decide the true value. But someone said that it is not a statement, so it's a repeating answer. So it's not a proposition because it's not a statement. Like you are like looping around, right? Because I define proposition and statement to be the same thing. Okay. And then the standard answer is like KFC's round state is better than McDonald's. Okay. Yeah, this is a proposition. Of course, you can have more creative one. Hey, who haven't got your quiz yet? You want to get that already? Who haven't? Please take photos and then after the class, give back your paper quiz. Okay. And then the third question, some of you like you don't know what I'm asking. So when is the proposition you make false? So proposition can be true or false, right? In this table here. So when the proposition is true, then not P is false. Okay. So bless you. So P is true, not P is false. So if P is false, not P is true. Okay. Only when the negation is true, then your proposition is false. Okay. So this is what the answer I want from you. So I want the negation of the statement. So actually I'm requesting for negation. Okay, when is your proposition false? When your proposition is false, then your negation is true. So question 1.3 is asking for negation actually. Okay, next. So next, I give you a particular example, right? So I want you to have ability to turn the example into some to fit into a general theory. So you need to be able to break the sentence into statements, okay, and then compound proposition. Actually, I give you a compound proposition here. So what's the compound proposition? Is the implication, okay, conditional statement. And then the other I want you to notice is actually this is a contrapositive, okay, contrapositive. So the question is asking you to show that the conditional statement is logically equivalent to the contrapositive. So there are two ways to show it because in class I gave you the two ways already. So one is either you show that the left and right have the same truth table, or you show that the biconditional statement is actually a tautology. Okay, two ways to show it. Yeah. So if you notice this one actually has a storyline actually. Actually I have part 3 and part 4, but maybe too long I take it away. Okay, maybe let's see what some of the interesting answer I received. What? I show in the start of the class, I think I show one. I show that, let me see. Okay, can everyone see or not? Yeah. So these are same type of people. So they tell me that when it's false, when someone think it is better, then it's better. And then this one, I don't know. to be honest, in my homeland where I born, there's no Indian Muslim there. Yeah. Actually, I don't need you to know what is Indian also, what is Muslim also. You also should be able to answer that question. Okay. And then, yeah. Yeah. I don't even care there exists a Muslim or not. Yeah. Don't care. No need to know whether there's such thing or not. Logic is always true one. Yeah. And then the second one, this one is a bit, I don't know, out of content. Suddenly come different things coming up. Okay. But something I want to discuss is quite good here. Some answers are quite decent. So let me show you. This one, yeah, yeah. This is topic about equivalences. Okay, so somebody changed my question, so they changed to bigger. Okay, maybe they like bigger drumstick, right? Or they think it's bigger then better, or cheaper the better, or what? Let me see. Or yummy the better, bigger the better, delicious the better. Okay, yeah. So this is equivalences. So if they're equivalent, then okay. If not, then you should be careful. I don't take off your mark for this time, but be careful. Okay. So yeah, even you don't even need to know what is better. So that's why, right? That's why it's very important. So you are a computer science student, right? So when they create this robot, actually it's very hard to create feeling for robots because robots are built up from logic. So they don't know what is yummy, what is delicious, what is better. They know better, but they also know not better. Right? So yeah. So hard to create feeling for the robot. Yeah, this one is some very quite good one. Some use the P and not P for the proposition. And then I say it's a never false. So the question will be never false. And then some also use contradiction, P and not P, always false. Yeah, always false. Or never false. Okay. This one put extra condition. Or this one is quite quite realistic because it put maybe weekend more people better or less people better. So yeah, or something wrong here, but never mind. Okay. Yeah, just some okay. And then the next one, uh someone use the quantifier. That's fine as long as you define it. You start with this and then you define better is greater, and then the other one is less than. But don't straight away use this because this is not understandable. Okay. And then this one, this one quite good. If you prefer Indian cuisine, Mamak's is better than KFC drumstick. This one's good sentence. If you prefer, yeah. So what's the negation? When you prefer Indian cuisine and KFC drumstick is better than okay. And then this one, this one not only answer the question, also still ask you how to check it. Yes, very good. The boss will like you alone. Tell the boss how to check. But this one very creative. This one, right? What about me? If KFC drumstick is better than Mama, then Kisen will go for KFC drumstick. But my name spelled wrong here. I don't take off my. Uh, Actually, in fact, this is the how to say. This is where I get the idea for this question here. So the first day I arrived here, somebody bring me to the Mama restaurant, and then I tried the drumstick, and then not so good, but very expensive. Yeah. So that's what where this question comes from. Okay. Okay, any question? Any question for the quiz? Okay, please take a photo and then give me back after the class. No question? No question? Then try to do today's tutorial and then we will discuss at 6:35. Yeah. Is anyone haven't signed your attendance? Yeah. Is Yang Yue here? Yang Yue. Okay, visa problem. Yang Yue. Ấn Sinh Yuan and Wang Han. Okay. Is hello? Hello. Is anyone friend with the absence today? You have to help them to take photos. Anyone friends with them? No? I noticed some of you use the Chinese translation text, but you can use it as a reference, but make sure you also read the English one because the English, I mean, the test is in English, not bilingual, no Chinese question. Okay. You can use your Chinese text to help you understand the English, but make sure you also look at the English question. You want more times or we discuss? You want more time? More times okay. 5 more minutes. Yeah, hello, hello. Okay, let's discuss now, otherwise more time. Okay, so let me know if you have different answer, okay? Then we can share answer. So first one, okay, this is actually they call, if I forget to mention to you, this is called the rooster method. Roster. And then this one is the predicate to set, right? Just now we introduced it. Okay. So when we look at a set, right? So usually the set has some pattern. Okay. For example, in this case, we got 0, 3, 6, 9, 12. So it's like multiples of 3. But multiple of 3 is just like 0, 1, 2, 3. Okay. Restrict the multiple. And then the next one, what do you have? What you observe is actually there are numbers in the integers. This one I also can restrict the domain. Maybe I restrict the domain to, I think to R to Z. No, maybe not. To N. Okay. And then MNOP. It's a letter from this one. You can find it from there or any other places you want. Okay. Any description you like. If you have different one, you can speak up. Okay. Speak up. Okay. Okay. Next one. So if you know the definition, maybe it's easy. If you don't know the definition, maybe you're confused. So is there any question, like any sub question that you want to discuss? Any particular one that you really confused? If all of them are confusing for you, then pick one to us, right? Any particular one you want to discuss? Just now, Sancho asked me about this. Are this equal? Anyone know? Huh? Yes or no? No. Why? Huh? Why are they not equal? Huh? What? Say again, say again. No, both of them are the same. Both of them are same. This one is empty set. This is also set. This is set of empty set. Both of them are set. So why are they not equal? Go back to definition, right? So definition, you need to show that the left is a subset of the right one, and the right one is a subset of the left one. Okay. Okay. Yes. Okay. So this one is always correct because we already proved in class. It's a theorem. So every set has two subset. One is empty set. One is the whole set. At least two. I mean. Okay. But here, phi is in here, but phi is not in here because empty set has no element. Yeah. Any question you want to discuss here? If not, we jump. Or next week, you also can bring out the matter if you want to discuss further. And then 2.1.22, yeah. So the cardinality of empty set is 0 because nothing is in there. Here, just now we already said this is a set with an empty set. So empty set is the element, one of the elements. So here we got two elements. Empty set and the set of empty set. Here is three elements. Remember this arrangement here? Last time I talked about how they construct the real number through the piano axiom. So this is similar. There are one thing 0 here, one thing here, 2 here, 3 here. Right? So this is represent 1, represent 0, represent 1, represent 2, represent 3. Okay. Yeah. Okay. That's why, yeah. So, yeah. So did I told you how human create natural number through counting shifts? Did I tell you? No? So what do you call them? The the person who read the shift is called what? Suddenly forgot. Anyone know? Okay, never mind. Then next 2.1.24. So if A and B has the same power set, are they equal? Yes. So if you take the union of power set, it's just the set itself. Okay. Otherwise, you can prove by contrapositive, right? So if this, then they're equal. So suppose they are not equal, then that means there's an element that's not in the other one. So you can produce different power set. That's also okay. Contrapositive. Okay. Okay, next. 2.1.26. Forgot what this question is. Okay, so this question asks about whether this set can be a power set of any set or not. Okay. A cannot because power set of every set include empty set, and okay, the power set of every set include empty set. Okay. So it cannot be empty set. Must at least contain empty set. And itself. That's what we prove. And then B, this is a power set. Okay, power set of who is a set that containing A. C cannot because only got 3 elements. It's not a power of 2. Yeah, okay. Because you also can produce this set, right? So you add in this set here. Okay, this is what is done in B. Okay, this is the power set of A, B. Okay, 2.1.50 is a very famous paradox, Russell paradox. So you assume there's a set, okay? There's a set that contain this the element inside the set is not an element of itself. Okay, the English is like that, right? It's not an element of itself. So suppose X is in X, then by definition, X is not in X. So contradict with your assumption. And then suppose S is not in X. Okay, you follow this, you obey this predicate, right? So that means X is in the set itself by definition, but still contradict because contradict the assumption. So the moral here is you need to stack where your domain live. Okay, you can't simply just consider all sets. You need to set a specific domain, okay, somewhere. Okay, next. 2.2.4 should be quite easy. So compute the union, intersection, difference. 2.2.12 is where I want you to practice the set equality proof. So you show the two set inclusion. Of course, you also can use the membership table, but I want to emphasize this method here, set inclusion. Because this combined with the predicate logic. Next one, 2.2.16. 2.2.16 also practice on the set inclusion proof. How you combine the set theory and predicate logic. Okay. E, so the same. E actually got one part I don't know, but I think cannot directly prove, so I use the contrapositive. So that's mean if it is not in here, then it's not in here. If you can do the direct proof, you can tell me. I can include here. So I use the contrapositive. So I use because I want to show that if X is in here, then X is in here. So to show the contrapositive is if X is not in here, then X is not in the other one. We use contrapositive. Okay, one more. So this one is similar to what I gave in the class, the example. So Really interesting one to discuss. Okay, this one 2.2.56. So if you take, okay, this one is getting smaller, right? So when I greater than this one will like getting smaller, shorter and shorter. Okay, if you take union, is everything A1. But if you take intersection, it's going towards infinity. So, but if you reach infinity, infinity is not real, so nothing here. How about this one? This one is growing. If this number is bigger, then this part is not growing. I mean, it's like 0, 1, and then 0, 2, 0, 3, 0, 5, 0, 6. So if you take all of them, you include all the, you got like a lot of, cannot say multiplicity of 0 because it's not multi-set. But in set, then we reduce the multiplicity to 1. So it's actually just the natural number. And then if you take intersection, so 1 is not in the other, 2 is not in the other. So only 0 is in every set. Right? So 0. So actually to be precise, you can show the inclusion, set inclusion, like what I did in the class. And then this one we change it to open interval. In the class we did close interval. So okay. And then similar of this one. So if you take intersection, if you're getting when this I getting bigger, then it get closer to infinity, right? So this interval getting shorter and shorter, shorter and shorter, shorter and shorter, 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 okay, to nothing. Okay, infinity is not included. It's not integer, it's not real. Okay, normal. Any question you want to go through again, or you got question? Or if not, then you digest and then you bring it next week. Then please hand me back your quiz before you leave.
同学先回来，我把他的拍一下。
可以。你刚才我不是有问吗？根本没有回答。没对过，哪个是女同学？
上题会。
是啊。他有没有那个发邮件给我？呀，这个是3啊，是因为这个也对，其实它就是开一格呀，呀，我是 A1，因为 one 是最小的嘛。这个吧？什么？它不是到9呀？这个是 intersection 呢？说你01吗？01、02、03、04、05、06、07、08，所以01是在所有的里面，对不对？明白吗？那我画给你看吧。知道了。说呀，说 01吗？01, 01, and then 02, and then 03 嘛，right? So all of them are contained. So if you take intersection, then everything here is in everyone. 只是在招呼人，yeah，对吧？是语言，对吧？对吧？对吧？是楼上的是在楼下吗？在楼下里面，在楼下对，楼下的在楼上面，现在所以你拿 intersection 的话，只有它是在全部里面，对吧？因为你拿3的话，3就不在这边了，3也不在这边，对不对？ 对吗？
I still can't understand the differences between the
Which one?
bracket or
Which one bracket and bracket? Which bracket?
the this bracket.
Uh-huh.
The 那个空子也是 bracket.
See bracket. You want to go
This and between.
Oh, okay. So you want to ask this one?
What is the differences?
What's the differences? What's the differences? So you want to ask whether they are equal. Right. So to show they are equal, you need to show two set inclusion, right? So you need to show that these two set inclusion. Okay. I mean, if it is true, then you need to show these two. Okay. So, but this is always true because every set contain empty set as a subset. Okay. But how about this one? Okay. This one, if you want to show this by definition is what? Every x in here implies x is in here.
Yeah.
Where? Okay. No, I give you the general one. So x. Yeah, this is what you want to do. Okay.
To show that this is true.
To show that this is true. Okay. Right? Then okay. Okay. So what is in here? So you can take x equal to empty set. But C is not in P. Empty set is not an element of empty set. You know why?
Because it's not
No. Because by definition again, V doesn't contain any element.
so
Ah,
so it
Ah.
didn't have
anything.
anything.
So this one wrong. So that's why this is false. Okay.
So can explain like B
B.
actually. Oh
B. This one B.
no, this one 2.2.
Oh, this one.
Yeah.
Oh, this one is just set. It's not interval. So there's only two things here. Either 0, either R.
How come the bracket one is curly?
Okay. This one this one a bit sloppy, so this one is actually curly as well. Yeah. Okay, there's no such thing like this. Okay. This one either I draw wrong only. Only can like close or non-close can. But not for the set. Not the curly.
So I is a variable or is it like
I is a variable.
also it's not like imaginary now.
No. Here. I already said I is an element in the integer.
One is like
Mhm.
0 and 1.
Yeah.
Like the side of 2 is like
0.
0 and 2, so it's
Yes.
only 0.
Yes. So like this. So 0, 1, 0, 2, 0, 3. Oh. Yeah. Thank you, sir. Okay. 来，
我问一下，这三个符号
呀，怎样？
它有什么区别？
区别什么意思？
就是比
听不懂。
如说
嗯
这两题它
Yeah
都是一样的，但是除了符号不一样。
哦，OK，呀。
嗯
OK，这个区别是什么？
嗯
这个是说这一个在不在这里面？
在
不在，
不在，
在吗？
对我想想，
不在，
不在，
不在。
不在，
你可以查一下，应该是不在，所以是 false。
嗯
这一个是什么意思？
这个是说这一个是这个的 subset，
哦，
对不对？subset 的意思是什么？每一个在这里面的东西都要在这里面。
那所以这个前提条件，这个要是一个 set，就是用这个
啊，对对对对对对对对对对对对对对对对对对对对对对，
不是个
就
set 就直接
不能
false。
讨论啊。但是这个是个 set，这是 empty set，
对，
对，就可以讨论。
嗯，
所以，但是你要讨论，你要从这个 definition 咯。对对啊，是对啊，是。对，每一个这边里面的东西都在这里。
那是对的。
为什么？
空集
嗯，对，
空集里面包含的 element 就是 empty，
对，然后所以，
然后 empty 包含在，
哎，不是这么说，不是这么说。
不是这么说。
因为你要说每一个这里的东西都要在这里面嘛，
嗯，
这里面没东西嘛，
没东西。
这里是 false 嘛，false imply 所有东西，可以明白？
诶，
嗯，再讲一个。
有点没有绕过来。
嗯，所以这个意思是什么？
嗯
这个什么？这个意思是说每一个这里面的东西都要在这里面，
嗯
对不对？
嗯，
那这里面有什么东西？
没有东西。
没有东西啊，没有东西就不能讨论了，因为它是 false 嘛，false imply 所有东西，懂什么意思？就是不管你犯对的错的东西在这里，这整句话都是对，
哦，对。
对吧？对吧？对吧？对吧？
哦
啊，
哦，
所以换另外一个话说，换另外一句话说，像你说，就是你没有东西好讨论，就是没有东西在里面，这样就自动在里面。
嗯，好，还有这个呢，
这一个
下面加一个好。
哦哦，OK，我有讲过这个嘛，
嗯
这个是 proper，这个是 OK，这个的话就要说，
嗯
你要找一个这里的东西，
嗯
不等于不在这里面，
嗯嗯，
就是它没有可能会等于里面
哦，因为是呃，它是它的 subset，但是它有可能 A 等于 B。
啊，对
那如果下面一个横杠就是不能等于
对
啊，
啊，对，这
懂了，
个就是横杠咯，它没有横杠呢，它就丢掉那一个，
就不能就不能等。
不可以等于，对，
好，
不会等于，好，
懂了，
对，好，
谢谢，
不会
懂
，OK，
了。
可以。你是哪里人哦？哦，你是厦门人，OK，好多厦门人呢，这里。嗯哼，会不会厦门口音转马来西亚口音比较浓郁？是吗？对吗？因为我以前同学在北方啊，他听不懂哦，有些，对不对？北方和南方还好。哦，你妈是北方人，哪里？山东啊？哦，辽宁啊，东北三省。OK，好啊，不会，